algebra. We're going to talk about algebra. Everyone gets twitchy about algebra. I love algebra. Algebra is a tool that solves problems, and therefore it's a solution. So algebra is a solution to life, the universe, and everything. Maybe that's an overstatement. I think God probably is, but from a Christian worldview. But in terms of maths, algebra is right up there. So let's have a look at a phone plan and see what we can do. So I've got a phone plan here, so let's pull this up. And we're going to have a look at, well, the Felix, the best prepaid phone plan. So was algebra relevant for that? And they're saying it's 17.5 a month. Well, it is, but not for the whole 12 months. How much would 12 months of, use of the phone actually cost you? So let's try a few things. Okay, so we're going to flick a bit. There's Felix. So we've got 17.5 months, 3 months, 35 months thereafter. In fact, I went into the website and it shows you that actually, yes, it is $17.50 a month, but it's because they're applying a discount for the 50% off for the first 3 months. So let's maybe use that concept of a 50% off for that. So back to my mobile phone plan. Let's see what that would perhaps look like. Well, I'm going to use the M for equals the M is the month, and that's the dollars per month. And that's a known fact. So it's $35 per month and is the standard charge, but they gave 50% discount for 3 months. So I'm going to say it's 3 months divided by 2. That's 50%, isn't it? Or it could be 0.5 if you wish. So we could say 3 times 0.5 plus, it's going to, obviously the balance of that is 9 months at $35. Plus 9 months at $35. So in 12 months, that's what it would cost us. So can I simplify that mathematically? Well, can you see 3 over 2 is 1.5, and 3 times 0.5 is 1.5. So it doesn't matter whether it's a fraction or it's a decimal. Let's stick with here. Both of them will equal, well, that's 10.5 M months. And effectively, you're paying like 10.5 of the full month's price. So what's the answer? The answer equals 10.5. What is the month? The dollars per month, which was $35 per month. And we can work that out. Let's pause my video. If I can find the pause button, don't know. So that's 350, if that's okay, plus $17.50. So that's $367.50. Not bad for a plan, is it? But let's go back to our website. It is limited in terms of its speed. So if you want a lightning fast one, perhaps we have a look at this one here and see how much difference we would pay over 12 months to get the lightning fast circles.life one. So it is, let's go back to its site and have a look what it actually says. Okay, so it's got good, it's got a lot of data you can have. It's got bonus data for you for 6 months, and your bill waiver, $17 off that. But there's your price per month, which is there. So it is 6 months with $17 off the month, and 6 months with a full price. Okay, so let's take that back and have a look at it in an algebraic sense. And I'll just make a little here that the month, and that is equal $35 per month. That's the monthly price. Okay, so M for this, same thing, is the month per price, equals $45 per month. So we have 6 months at the monthly price minus $17. And then we have 6 months at the monthly price that we have there. So if I have a look at that, it is 6M minus $17 per month. So it's actually 6 over month minus 17 plus 6 months. So if I, using an algebraic law called the distributive law, that is 6m minus 6 times 17, so 6 tens are 60, 6 sevens are 42, 100 and minus, $102 plus 6m. That will equal 6m minus that plus, 6m plus 6m, that's 12m minus $102. So it's going to cost more perhaps, because you can just look at the mobile plan here and you say, well, it's the monthly plan's more expensive to start with anyway, and I do get some off, but that's lower as well. So this is going to be cheaper, the Felix plan, absolutely. But I want to know how much it's going to cost me per month for a 12-month time to get that higher speed. So let's work with that. Now that we do what we call substitution mathematics, we're going to put the $45 in that. So that's 12 times $45 minus $102. So that's 10 times 45 is 450. 2 times 40 is 90. So 450 plus 90, that's $540 minus $102. So I minus 100 and off that, and then I take another 2 off as well. So we have a look at what we have, and I made an error, so I'm going to just correct all that. That was minus 102 here, minus 102. Take 100 off, that's 440. Take a further 2 off, that is $438. So $438 for the total 12 months versus $367. So how much is that? Well, it's obviously more expensive, but per month I've got to, we could work out how much am I paying per month to get a better speed and maybe some great amount of data. So let's do it roughly. That's about, let's say it's nearly 70, so it's nearly $30 to get to 400 plus another $30 or $40 there, so about $70. Round about $70 extra per year to get more data at a higher speed. What about you? That's not too bad. And there's 12 months, so it's $6 a month. I don't think that's too bad. I'd probably go for that plan. Even though it is more expensive, it's not that more expensive for that. So what do we do here? Well, so we had a look at this here. That might stand out, the Felix model, to be really, really useful for you. Now, when we build the speed into it, that makes a difference. But overall, it's not that much more expensive. So that's algebra solving a problem. Now, there's other ways to do that. You could just put the numbers in and it's 28 times 6 plus 45 plus times 6 and so on, and use that just straight numbers straight back in. But when you want to manipulate things and start talking per month or what that rate's going to be overall, algebra can actually assist you. So it helps you decode in life using mathematical skills and so on. So I hope you enjoy that little exercise that demonstrates how you use algebra in solving problems in the real world. Let's look at a different scenario. One of my students in my classes is getting married. She's engaged. She's going to get married this year. So maybe we can help her with her wedding. Now, the River Life that's on the river, they're a lovely spot. So, great looking packages they've got, different packages of different, look at that for venues, different marquees. Get 180 seated, 80, 100, and so on. All different size places and venues. So, different sort of packages. You can get the ceremony. So let's see if we can help her and make a little sort of an assumption. So let's look at 2 things I prepared earlier. So let's look at option A. It is, you've got here 120 guests, $15 drinks, 2 drinks for that, pay for the rest. It's a bit cheap, isn't it? But anyway, that's all it is. $1,500 for the venue hire, and the food per head's $125. The other option is a different place within the venue. It only holds the 80 comfortably anyway, slightly a bit more, but 80 comfortably. $20 for the drink package for and it's only $1,000 for the hire because it's a smaller space. The food cost is exactly the same. But if you want extras, you're paying $125, $35, and $130. Now, the thing is, they want, what they do want is 100 guests. So how do we work out which one perhaps would be cheaper for them? So let's have a look at what this would be using some algebra. So you can't, if you know you've got 100 guests, you still have to pay for the 120 guest package. So the left-hand one is option A is not too difficult in the sense. So let's work that out. It is 120 at the food price plus 120 at the drink rate D plus the hire for the venue. Because we define those terms, they're called variables here for both. Okay. Now, if you had a different venue, then perhaps that would still be the same, whether it was River Life and so on, no matter what. Food, drinks, and hire your main costs. So can I simplify that? If I've got 120 Fs and 120 Ds, well, I've got 120 F and Ds, haven't I? So we can simplify this. It's 120 for the food and drink together. So it's 120 times that, plus the venue hire is just one set cost, isn't it? So what's that equal? An algebra was set out equally. That's the total price. So we go back and say, well, how much is that? Well, it's 125 for the food and 15 for the drink. So that's 125, 15 plus 125 plus the venue hire is 1,500, sorry. So that's substitution. Now you're putting the numbers in. So we look at that. Let's make it a little bit easier. That's 100 times 140 plus 1,500. Oh, so let's work that out. Maybe you just do it in your heads, although I haven't got that luxury. So let's go. So I've got my handy calculator out, and that is $1,680 for that, plus the 1,500 here. So let's go. So 0, 0, 0, 0, 8 is 8, 5 and 6 is 11. Put one extra. That's $3,180 for 100 guests at that venue for food and drink. That's pretty. That's not too bad in terms of price that we're looking for. Oh, that looks too cheap. Of course it is. I thought I'll have a wedding like that every day of the week. Made a big mistake. I times it by 120 by 14. So that's it. That's slightly bigger, $16,000. That seems more like it. So let's undo that. Let's now add it up. So 0 and 0 is 0. 0 and 0 is 0. 5 and 8 are 13, carry 1. 1 and 6 is 7, plus the 1 is 8. $18,000. That's more reasonable. That's how much weddings costs. Okay, now let's go to the same operation here for the 80 guests, but they want 100. Okay, so it's going to be, the drinks are slightly more expensive for the venue wants to make its money, but it's cheaper on the hire. So let's put those things in. So it's 80 food plus 80 drink, okay, plus the hire, plus 20 more guests, extras, times 135. Now, in that package, it's a slightly smaller venue, so people will be a little bit squashy. In the option A, they'll be spread out a bit more. But let's see, it's all about comes to the dollars. So then we do the same thing here. That would equal 80 food plus drink, plus the hire, plus 20 times that. So let's do the 20 times 135 to start with. 20 times 135, my calculator on the side here, that's plus $2,700 for those 20 extra people. Let's shorten that up, that's 80. F plus D, let's do that straight away. That's drink is 20, food is 125, so it's 145. slightly more expensive, plus the venue, slightly cheaper, plus 1,000, plus the 2,000. And notice you set out, you keep bringing the terms down into use simple. So let's have simplify it. So it's 80 times 125. So 145. Okay, that's the 11,600 plus the extra 1,000 plus 2,700. Ooh, which one's going to give the better option? Well, quickly I can see that's 12,600 plus, ooh, here we go. So 12,600 plus 2,700. I can do this in my head. Can you join me? 12,600 plus 2,000 is 14,600. 14,600 plus the extra 700 is $15,300. There you go. It's actually going to be close to $3,000 cheaper for that price with this option. Now that seems surprising to me, so let's go back and check that we've got all the details correct, because algebra has solved it, and maybe first thoughts, I thought maybe the bigger venue with the cheaper drinks might have been the better option, but let's have a look. Now the numbers seem to work. So food and drink, 145. Yeah. Food and drink, 140. Yeah, that's all working. So the difference, of course, is you've got 120 versus 80. That's a significant difference, isn't it? But, you know, the compromise is, you're getting a smaller venue. People are going to be a bit more crowded in. You haven't got the quite same river views. So it's $3,000 difference. And that's where you'd start to say, is that worth it? And perhaps, you know, if you're money conscious, then option B is the better one. If you're not so money conscious or tight and you want the premium venue over the river, then perhaps the $3,000 is worth it. And you think, well, what's that mean for $3,000? Well, $3,000 with 100 people coming to your wedding, it's $30 extra per person, isn't it? You might say, yeah, that's it. This is a great day. Or you might say, you know what, I can bank that $3,000 and put it down to upgrade the car, put some money towards the home, and so on. They're all the choices that you make. However, we solved it with algebra. So, on first impression, you might say, well, I get more, drinks are more expensive. Oh, better not do that. Although that's cheaper, and that's more expensive with the hire. But it's not just the $500 difference in the hire, is it? That ended up being the case. So all these things, these skills, these substituting of numbers in, this manipulating numbers and solving problems, all works out using this concept of algebra. And that's what you're going to learn about in this unit. The rules, the methods of solving problems. So we're going to go skills first. In the small subset of skills, we can then apply to the bigger picture of solving problems in the real world, and that is algebra. That's the main part. The next part is actually graphing, and we might go through a few little things on graphing now. The first part of graphing is actually creating graphs and interpreting them. So let's go to, and then usually a graph is the same as a table. It's just a different way of displaying the information. So you'll see graphs in a whole lot of ranges, statistics, you'll see graphs in science, and you'll see graphs obviously in mathematics. But anytime you've got information, it can be represented as a table or a graph. And sometimes it's more easily understood as a graph, or sometimes it's more easily understood as a table. So the graphs that I'm going to do are line graphs. If you have two sets of numbers, it's a line graph. If it's two separate categories that are not related by number, say blue, green, yellow, etc., they're not numbers. Therefore, you do a bar graph, or sometimes called a histogram. So, and you can use pie graphs as another sort of graphical representation. There's a whole lot of other twists and turns, but these are a simple one. So let's have a look at this. What we're looking at is about athletes' performance. Now, 100% is absolute blinding performance, and of course in 0, not so good. So they have a look at the idea of how performance is influenced by stress. So I've made some dummy data up there, but I know the answer. So let's now plot. So this is on the left-hand side, by convention, is what they call the x-axis, and this is the y-axis. The x-axis goes horizontal, so this is the x-axis, and the vertical one is the y-axis. So it's the level of performance. And sometimes we go a little bit deeper, the dependent and independent variable. In other words, the performance is dependent on the stress. The stress isn't dependent on the performance. Stress makes performance, not the other way around. So the dependent, the one that influences the vertical, the advanced one. But anyway, we've got stress levels. We've just categorized them 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. And here's our result. In other words, optimum performance. And they only got it up to 82% today. So in stress level 1, it's 35. And here's my 50. So I'm going to do it roughly and say it's round about there. And stress 2 was 57. Go 50. I'm going to go, it's about there. 3, mid-range stress, 82. I'll go about there. 4, higher level stress now. We go back to 53. I've got 53 here and there. And 27. It's the lowest one altogether down here. Now I've got those plots, or coordinates as it's called, so I'll now join them up and make it into a line. Great, that's what I want. Excellent. So I join those dots off, I plot like that. So here's my performance. Now the first one, as we said, let's make that a little bit more clearer, was to create. So it is taking from a table, drawing a line, having a scale, and then creating. Now it doesn't always have to start at 0. It just has to start below your lowest number, and it's just got to be above your highest number. That's 0 to 100, easily understood. So let's do that. So this is a range of data, it's called. So what's this tell me? Well, the answer is to often look at the highest and the lowest, or the left and the right. Well, the highest one, if we look at this point here, is the best performance, isn't it? It's like the mountaintop performance, and you can use that analogy of mountains and steepness and so on. So the mountaintop performance for athletes is when the stress is in the middle. So high performance, and it's mid-stress. That's what that tells me. And it says the lowest performance, low perform, so P is high stress, S. And it's also low down here, low stress. So this is low performance, low stress. Now, what's that telling me? Well, it's telling me if I need a certain amount of stress to perform athletically. And the same with sometimes study. I need the stress and the deadline to make me perform the best. However, if the deadline is in 1 hour's time, I am ultra stressed out here, high stress down here, I'm going to get low performance. However, if my assignment's due or something a month's time, I got really low stress down here. And if I'm not really motivated to perform on this task. Well, some of you might. I hope more of you have more lead time. Just when you've got the right balance, it's due in a week or 2 weeks' time, mid-level stress, I'll get the best performance because I've both got time to think about things without the pressure of getting it done really, really fast. So that exercise in athletics also can apply to things like study and life. So you need a bit of stress in your life, but not something that overwhelms you, and not so cruisy in life that you end up being lazy in life. And I think God gives us those experiences, and normal life gives us those experiences. And, you know, the right balance is what's needed in life. So that's an example of plotting a graph, then interpreting a graph, looking at the bottom, the top and bottom, and also left and right of your graph helps you interpret what's going on there. Now I've just redrawn that graph without the X and Y axis, but something that really intrigues and is very important is the fact that the slope, or the gradient it's called, or the steepness, is really important to understanding what's going on here. So let's have a look, and I'll use a different color. The angle at this point here is that angle. The angle at this point here is that angle. The angle here is that angle. And then it goes downwards, doesn't it, at a certain angle. So at this point here, here, and here, and here, they're all slightly different angles. One is uphill and one is downhill. Some are quite level in a sense. It's leveled out. You can imagine if you're riding a bike or running up a hill or walking and so on, that's quite steep. Less steep, it's flat for a while, and then it's downhill. It's going to help me. So that is called a slope, or sometimes called a gradient. Now, that is important and helps you as a bit of a key to unlocking some graphical information. So I'm going to simplify that graph into just a normal straight line type effect. So let's see how the slope plays into some thinking. Now over on the right here, I've drawn two straight lines and drawn it on my own little dodgy graph. Here's my x-axis here, and here's my y-axis there. So they have a certain angle. Obviously you can see that the slope, or the steepness, or the gradient is sometimes that, is of the purple line is more than the blue line. So, you know, they both intersect here at a point in y as is 1. So they both start or cross over at the same point of the 0 line, but one is steeper. So the answer is it's gone forward 10 lots. I wonder what it would be, the final answer, when it's 20, for example, when that's 20. Now that's the x. X, for example, let's take a point, maybe x equals 5. And x equals 5 crosses there on the blue line, and it crosses here on the purple line. So that's on the x-axis, x equals 5. So how can I decode? Now there's a rule that is applicable to all straight lines. And that's why I love maths, because it's one rule fits them all. So y equals the slope, and they use the letter m, times x, plus where it crossovers, and they call it the y-intercept is c. Why do they use m and c? Don't know the answer to that. But that's the convention. So that is a rule that we can apply to all straight lines. So how high it is, y, is equal to the slope, that steepness, m, times the value of x and c. So let's check this out for our purple line. So in our purple line, let's see what that means. So the first step is to work out what the angle is. So we have A and B, so we've got 2 points, so we can see it's an angle. So when you go an angle in steepness, you go up, don't you? But you also go forward. Now if you go up a certain amount, but it takes a long time to get there, it's going to be quite shallow, like blue. But if I go forward the 5, I've gone up a long way. That's called the rise here. This section here, I'm going to be now, let's see, I have a different pen. Between A and B, I've got that. This is how high I rise. This is how far I run forward. So the steepness is there. Notice that for the blue line, I run the same way, but I rise less. That's easier. But I'm talking about the purple now. So to find the slope, I've got to actually look at the angle between A and B. So I've got to find out what the difference is. The difference in height and the difference in run. So the slope equals how high I go compared to how far I go forward. It's run. Now the rise is, for this one here, what did it go forward? It's this much, isn't it? That's my rise. So it started off at 1 and it ended up at 7. Notice that's the difference between the y's there. So the rise was 6 and the run was 0 to 5. 0 to 5. So that is 5. So that is 1.2. So the angle is 1.2. Then I can put that 1.2 back into here. It's m. Let's now rewrite that equation. Y equals 1.2x plus c. Now c, we know, is 0. So plus 0. That's excellent. I can just rub that out. I don't need it now. It's saying, in this purple line, that every time I go up, y will go up 1.2 times the x. Now, if y goes up x once, that's actually a 45-degree angle. Think about it for a while. Pause the video if you need to. So slightly steeper than 45 degrees. But that's saying for every time I go forward 1x, I go up one value in y. So I'm actually going taller than I'm going here. Now let's choose a similar situation, this time for my other line, my blue line. And its rise and its run is only that far over the 5. And I've got to now choose, I'll call that A there, that A point here, because it's different. It rose only between here and here, and that was 1, 2, 3. So that is 3 in the y here. So now doing the same rise and run, let's rub out our working for our previous. We see the rise, it went up between 1, what happened there? Not sure what's gone on there. Something's deleted, my apologies. Let's see if I can get my video. One of my y-axes got deleted. So rise and run, this time I'm going to, what is the numbers here? Well, I'm going to call it A prime. So there, it is 5 and 3. 5x, 3y. 5x, 3y. And B, 0x and 1. And notice it's gone up between 3 and 1, the difference here, which is 2. We see it's 2 here. The rise is 2. And the run is still 5, isn't it? 0 to 5, 0 to 5. So 2 over 5, that's 2/5 equal 0.4. Substituted in, y equals 0.4 x plus the c. C, still 0, where it crosses over, it's 0 point. Let's get rid of that again. So this is saying that for y will go up 0.4 every time x goes forward 1. And if I, excuse me, at 10, at 10 then, if I put at here, what will it be here? Another little error. Sure, why? So if I say x is 10, what will it represent? Well, let's see, at 10, let's see if I dodgy what it'll be here. What will that be? Well, we can put that number in now. Now that's the equation for that whole line. That's its equation. So I'm going to substitute in. What would y be if x equals 10? Y equals 0.4, put x, so that's 0.4 times 10, and that will be 4. So if that's the case, yes, it is 4. So y equals 4, you can solve a point. Now, that equation, y equals 0.4x, might be related to a natural phenomenon. It could be how much the energy output might be per gram of coal or something. It could be what price you pay per litre of a product. Because that here is an equation. And that equation is obviously being measured and found to be true. And we can graph that. So you can what they call extrapolate that line forever. Both ways, actually. And you can use that graphical information to actually work out a rule, a solution to a problem. Now you can use graphs to find equations, or you can use equations to graph onto what they call a Cartesian plane, or a graph. So you can go both ways, and you'll learn about those things here. But a core area is that y equals the slope m times x plus where it crosses the y-axis, the y-intercept. And those rules you'll learn to manipulate graphs and to plot graphs and work out solutions. And we can see this measure here, 0.4, for example, is a measure of the slope of a line and how steep it is. In our previous example with the purple, we find it was a steeper slope, and it had actually a slope of 1.2, whereas this only has a slope of 0.4. So these are some of the principles and concepts that you'll come across when you're doing algebra. And algebra is manipulating numbers to create formulas or equations and substituting numbers in to work a solution. And also, it is also to graph that solution. But probably the most interesting aspect of algebra is balancing equations. And balancing equations and manipulating algebra is actually, I love it. But maybe you're not so familiar, and again, that's scary. It's not. Just let's learn these two simple rules. The first rule is that you do the same to both sides, and I call it my seesaw effect. So if I've got a seesaw, and that is equal, so let's say something's mathematically equal, it's balanced. However, if I do something, for example, I put a box on this side, which is 2 kilograms, well, it's going to be unbalanced. It won't be, however, if I put something which is 2 kilograms on there. What happens if I put something, if I then cut that in half? Chop it off, for example, like that, and just make it half the shape. Let's get rid of some of that. Well, it's now unbalanced. But if I did that, if I made that half as well, and did exactly the same to one side to the other, it would now be balanced again. So the first rule of manipulating equations in algebra is that you make sure you do whatever you do the left-hand side, you do the right-hand side, and it will still be balanced. And I suppose the skill and the art of using algebra is to use this balancing and manipulation of each side to get to the solution that we want. So I'm going to go back to a problem that we posed early on when I talked about numeracy, and it was talking about how many chairs you put around a table. So if you have a venue, for example here, you can sit 1, 2, 3, 4, 5, 6, 7, 8 people between the 3 tables. If I have 2 tables quite adjacent to each other, 1, 2, 3, 4, 5, 6. And if I have 1 table, I can fit 4 people. Well, how do I describe that in an equation or an algorithm for that? Well, we've decided here that, it's not, could be the number of chairs, okay, chairs that we have and we'll say chairs equals C. The tables that we have, we'll say is T. So T and C, I'll just tidy up my C a bit there. Come on. C is there. Can I represent that in some ways that I can do? So the number of chairs I can get around, or people around a table, is the number of tables. In this instance, I'd say times 4. Or I'll rewrite that 4t here. Here, I can say the number of chairs that I have here, I've got is I can get 6 chairs here, and I've got 2 tables. 6 chairs, so that'd be 3 times t, wouldn't it? There. The number of chairs on this one is 8, and I've got 3 tables. Oh, my error here. Error here. Rookie error. Sorry. Let's go back. This one here, I can 6 people with 2 tables. It wasn't a rookie error. It was right. So it's 3 times the number of tables. Here I've got 3 tables, and I can get 8 people. Well, it's not 3 times, isn't it? It's 2 point something. I'm going to say it's 3.7. It seems to be getting less and less all the time. Is there one rule that works Well, we looked at that and we found out that the rule that works is that actually the number of chairs and people can seat is 2 times the number of tables plus 2 on each end. So on here I've got 3 and 2 on the end. It's 2 tables with 2 and 2 on the end. 1 table with 2 and 2 on the end. So that is a rule that works here. This is a formula. It's an equation. They are interchangeable words. So that is a rule that will work. So the question I now ask is, let's say I have a venue and I'm just going to have one long table and I need to sit 86 people. I need 86 chairs. So the first step in anything is to write the formula down, then put the numbers in. So I'm going to put 86 as my total. So the question is, how many tables do I need? Well, I've got 2. This is my formula. It doesn't change. Well, I've got to do, now that is a balanced equation. It will work because the equation is right. So what I have to do is the same to each side. Now, I want to find out how many tables, T. So I've got to get rid of the numbers mathematically from around T. First of all, let's go from the things that are furthest away from T. It's 2T plus 2. So if I want to get rid of plus 2 from this side to get rid of it, I'm going to do in my thinking over here, plus 2, what can I do with mathematically? I'm minus 2. That will make 0, won't it? Or get rid of it. So I'm going to take 2 off each side, and I'll do it slow-mo. But if I'm going to make it balanced, whatever I do on the left-hand side, I must do on the right-hand side. So I took 2 off on the right-hand side. I must go 86 minus 2. It's now still mathematically balanced and correct. That crosses out, that's 0. And that equals 84 equals 2t. Well, 2t is over 4, and you're getting to see the answer is 42, isn't it? Life, the answer to life, the universe, and everything, by the way. It's a book that was written. Well, no, you may know it. So it's 2 lots of t. So how am I going to get t by itself? Well, I'm going to do the second rule now that is perhaps obvious. You do the opposite. If it's multiplied by 2, you divide by 2. See, it was plus 2, you did minus 2. So you do the operation that's opposite. So I'm going to do here, I'm going to divide everything by 2. Now, we never go divided by 2 like that anymore. We say make it a divide by 2 like that. So it equals, do it slow-mo, divide by 2. Which side? Both sides. So divide by 2. It's still now balanced. That crosses out, doesn't it? And I've got here on the end, I've run out of space. So I'm going to move my equation over here. So that's 42, and that's t. So the answer is, if I need 86 people in my venue, I'm going to set up 42 tables for that. Now that's a very simplified one, but the rules of a simple mathematics problem are still applied to a complex math problem. And the simple rules were this, that what you do to one side, you do to the other. And the other rule that we learned along the way is what you do here. You do the opposite function to simplify it. That's the rule of algebra. And I will sing you a song about it and how you do. The other rule is what you do with algebra. It's like the hokey pokey. You put the formula down, you put the numbers in, and you shake it all about. That's what you do. That's the algebra hokey pokey.